Hello everybody. Welcome to a video of the Lunar Mapping and Modeling Portal, which is a tool that will let you explore and learn more about the surface of the moon using data from the recent moon missions such as Lunar Reconnaissance Orbiter and other historical missions, for example, the Apollos and Clementines that you are familiar with. So you can use the LMMP for your school science projects, and it will be fun to share and show what you have learned about the moons with your friends and your siblings, parents, and also other family members. So let's get started here. In the browse mode, here you can click and basically drag and zoom and pan around and using the background mosaic here. And you would also be able to use the slider on the side here to do this basically zooming and panning as well. So by default, you're looking at a flattened rectangular view of the surface showing names of many moon features, and we call this the base map. And then you can also, if you point your cursor to the north edge here, you will be able to see the North Pole wheel. Or if you point it to the south, you will be able to see the South Pole. So Brian, would you please take us to some interesting features?
Sure, and that's going to be helped by the fact that we have this wonderful search feature in LMMP. So you can type the name of an interesting feature. So for instance, let's try the crater Copernicus. I'm going to stop right there. Let's do that again. But once you type in Copernicus, hit the little magnifying glass, and then it'll just zoom us right there to it. There we go. So here we are at the crater Copernicus. Big close-up view. Let's zoom out just a little bit by hitting that minus button at the end of the slider there. And we can slide out. There we've got a nice overview of this beautiful crater Copernicus. If you look, the edges of the crater are actually terraced. And this shows where fluidized rock flowed downwards from this tremendous impact. And if you look in the center, there are a series of mountain peaks. And these central peaks are from deep rock, about 10 kilometers down, that rebounded upwards after the impact that created this crater. This is a relatively young crater. It's less than 1 billion years old, and it's surrounded by a bright ray system of crushed pulverized rock that was sprayed out over the surface. Now, when I show Copernicus to people, one of the things that they always ask is, well, how big is it? And is LMMP going to be able to tell us that?
Yes, definitely. We have a tool here which allow you to draw a line, a polygon, or a freehand drawing to be able to show you the distance. So let's use the line tool and let's measure from one end of the crater to the other. And you will be able to see that it shows you that it's about 90.5 kilometer wide, which is equated to about 56 miles.
So going across the entire lunar surface, you can measure the size of features.
That's correct. So in addition, let's just remove this line first. Let's draw another lines that will cut across from one rim to the other and covering also the peak the center of the crater. And here you can click on it and be able to calculate the elevations of the craters, which here it shows up a profile. As you can see that from the beginning here, you can see the blue dots. When you traverse this line, it can actually tell you exactly where you are relative to the line, the elevations, as well as the distance from start of the line. So you can tell that, you know, the rim going down to the crater, and then right there in the center, there's the peak.
So that's amazing. You're able to measure the depth of the crater, and then anywhere along that profile, you can see the actual elevation.
That's right.
That is an incredible tool.
So let's try, remove that, and let's do a freehand drawing of the outer skirt of this crater.
So you're just kind of walking along the rim there.
Imagine your rover traveling around the rim here. So again, if you, whoops, you would be able to see calculate the elevation and look at the profile.
It's kind of this bumpy rim there.
There's a bumpy rim, and I'm not sure you want your rover to be traveling along there. But as you can see, again, you would be able to tell the distance as well as the exact elevation from each point.
So you can essentially trace any path you want on the surface of the moon and measure distance along that path, as well as the elevation.
Yep.
Okay, that looks like a good tool for planning your rover traverses.
Yep. So how about take us to something different?
Yeah, this looks fun. Let's try something interesting. Let's go take a look at a very different type of terrain. Type in Hadley, Hadley. So this is a very interesting area. As you look at it, it looks like a dry riverbed, but no water ever flowed here. This is a channel that was actually cut by flowing lava. It's a canyon that is very, very spectacular. As a matter of fact, the Apollo 15 astronauts actually visited this area. And one of the things you can see is it is right at the base of a large mountain front, the Apennine Mountains. And so one of the things we can do is trace a line. Let's do an elevation from the floor of the mare right there and go across. There you go, perfect. We'll go across the actual rill there, Hadley Rill, and then up the slope of the mountain so we can see both how the rill drops down and how the mountain front goes up. There you can see that trough of the rill right at the base of the mountain front there. So the Apennine Mountains are a very, very spectacular high mountain front, and you can see that trough of the Hadley Rill right at their base. There's another really good example of one of these that would be fun to take a look at, and it's right next to the crater Aristarchus. So let's do a search for Aristarchus. So this is the crater Aristarchus, and if we zoom out, we'll see that we're actually in an area known as the Aristarchus Plateau that is a fantastic volcanic area. There are a number of things to notice here. First thing we'll notice is right next to the crater Aristarchus, there is another crater, Herodotus, that is about the same diameter, but if you look at them, they look dramatically different. Aristarchus looks very similar to Copernicus. You see the terraced walls. But if you look at Herodotus, you see a very flat floor. What happened there was that the floor of Herodotus was actually filled by lava that upwelled from beneath. And we can see this pretty dramatically if we draw a line going across both of these craters. And let's do an elevation map like you did before. And here we can see both of those craters next to each other, and look how much deeper Aristarchus is than Herodotus. And so you can see the actual filling of the crater Herodotus by lava. But as we talk about lava, let's talk about the areas of volcanic eruptions that happened here. Above Aristarchus and Herodotus, you can see this long rill, this great channel. This is the greatest of the sinuous rills on the surface of the moon. And the lava that formed it was erupted from right there, an area called the Cobra's Head. You can see why it's called that. It looks like the head of a snake. So let's go ahead and let's measure the depth of that pit that the eruption came from.
Okay. We'll just draw a line across it.
Yeah.
And then take a look at this profile. This is very interesting. Look at this profile. See how deep this is in the middle.
And you can see
the
how
rail.
the edge is raised above the surrounding terrain,
terrain.
the buildup of lava around it. It's very neat. And one of the things you could also do is we can explore the length of the rill there. Because again, one of the things when people see this, they look in a telescope or they look in online atlases like this, the LMMP, is they want to know how long is this feature.
So let's draw a line from the beginning and trace it through this tube. Let's find out.
We can see the general downward trend. And you can also see the length. So how long a length did you measure, Emily?
It's from the beginning to end there, it comes to 145 kilometers.
Okay, that is neat. But let's take a look at that left end there. So let's go ahead and, if you look very carefully, let's zoom in a little bit. Well, look, there's a smaller extension that's coming out. If we remove that line that we drew, we can see something very interesting. If you look inside the main rill of Schroeder's Valley, there's a smaller rill inside of it. And that smaller rill continues past the end.
In fact,
So
it started from the beginning.
That's
you
right.
can
It
tell.
goes right through the Cobra Head. So we see two different eruptive phases here. The main broad rill was cut, and then a smaller rill from a later eruption cut its path through the main rill and continued on past that. Very interesting. And as a matter of fact, if we do just a shortcut, let's try, again, going right across the head of the cobra. And let's see if we can actually pull out the difference between that main rill and see the smaller rill inside of it. So here we're going to examine features within features. And there enough, you can see the big rill and then that little trough right in the center there of the smaller later rill. That's cool. That's neat. So we've been looking at sinuous rills, but there's another type of rill on the moon that's really interesting to look at. And let's see what LMMP can show us of those types of rills. Let's go to Hippalus, Hippalus. And if we zoom out a little, we'll see something very interesting. So that's a little bit further. And there, you see a series of concentric curving rills. They're not winding and sinuous like the previous rills. They are very different looking. And as a matter of fact, what we are seeing here are cracks in the surface of the moon. This whole area is on the edge of a giant impact basin called Mare Humorum. And when Mare Humorum formed, lava welled up through the cracks on the floor and filled this giant impact basin with lava. And under the weight of all that lava, the ground began to sink. And as the ground sank, the areas around the edge cracked. And that's what we're seeing right here. So maybe we can do a profile and see the nature of these cracks. Okay. So let's move along the edge there. You can see these cracks are very, very subtle compared to what we were looking at before. But also notice something interesting. So we go to the left, which is that Mare Humorum basin. We can see that the ground was lower in that profile. So if we bring that profile back up again, you can see how the basin shrunk down, or you can see how the basin dropped down. And as it dropped down, that caused extension in the surrounding terrain that formed those cracks that we're seeing.
Now, how big is this basin?
So let's zoom out and take a look. So there, you can see that dark circular area of Mare Humorum. If you wanted to measure it, you certainly could.
So this is much bigger than the other area basins that we looked at earlier.
So when we were looking at Copernicus, yeah, we were looking at something about 90 kilometers in diameter. So let's compare Mare Humorum to Copernicus. So again, you can
draw a line. Let's take a look. So this one is about 407 kilometers.
as opposed to the 90 kilometers of Copernicus. This was a much bigger impact. But you can see that it's almost completely filled in with lava. So remember what we saw with the crater Herodotus, we're seeing an even a more extreme example of that here. And then we have those cracks on that one side.
And Brian, I also noticed that there are additional cracks on the left-hand side of this basin here.
Right, so we can see the same type of process occurring not just in the area we looked at before, but we can see a variety of features around Mare Humorum. So there we can see some features that are very similar that appear to be extensional cracks. But if we go down a little further there, we can see some interesting rills along the floor of Mare Humorum. And this appears, notice how it's darker around them? The ground seems a little darker. That seems to be pyroclastic deposits. That seems to be material that was erupted onto the surface of the moon, coming out of these cracks that you're seeing.
Now, Brian, do we have any volcanoes?
Yeah, so that's a great question. We saw evidence of eruptions here, but there's nothing there that really looks like a volcano, is there? But let's go to something else. Let's go to a series of interesting, fascinating volcanic peaks. And these are the Gruithuisen domes. So here we are at Gruithuisen Delta, and right next to it is another one, Gruithuisen gamma. Let's zoom out, and you can see these are two big peaks on the moon. And these are interesting volcanoes. These are among the tallest volcanoes on the surface of the moon. The moon typically does not have tall volcanoes. That's because the lava that erupted on the surface of the moon was very thin. It was very runny. It had what we say low viscosity. It has the viscosity of approximately olive oil at room temperature, and it's really hard to build a mountain out of something like that. But here, with the Gruithuisen domes, the lava was apparently thicker and stickier, and so it was actually able to build real mountains. And if we draw a line through both of those, we can actually see the elevation profiles of these really fascinating volcanoes.
I'm actually draw a line across the crater next to it as well.
Very good.
So then we can take a look. That is a very interesting profile, Brian.
So you can see those two mountains standing high up
High
there.
up.
Compared to the depth of the impact crater next to them. And again, one of the reasons we can distinguish that crater is not a volcanic crater, it's an impact crater, is it does have that raised rim around it. A lot of times when we see volcanic craters, they don't have that kind of a raised rim. Many times, not always.
Interesting.
But these are very atypical volcanoes. Most of the volcanoes on the moon, again, were made of this much thinner, runnier lava, and therefore when they form any kind of an elevation at all, it's a much lower elevation profile. Let's go take a look at an example of a more typical lunar volcano that's right next to the crater Militius. So there's the crater Militius, but I'm not seeing the volcano. And that's unfortunate because the volcano, again, because it's so low, it's typically visible only when the sun angle is coming in very, very low. And here in the mosaics that were taken by LRO, the sun angle is so high that we're actually not able to see the volcano.
Well, no worry, Brian. The lunar mapping and modeling portal has many different layers to work with, showing many different aspects to the lunar surface. So let's switch to the LRO's Lola Dam, the DEM, with the hue shade layer. That will be able to give you a better look.
Wow.
Now you can.
So there, yeah, that's fantastic.
Yeah, also you will be able to see the features that you wouldn't be able to see earlier.
So there's the volcano now standing out very clearly next to the crater. And because we're using the laser altimetry data coming from LRO, we're able to see these very subtle changes in elevation. If you look very carefully, you can see that the lunar dome there, the volcano, actually has a crater right at its summit. That might be something interesting to profile.
So let's draw a line across it to take a look.
It's a good idea. Compare it to the profile of an impact crater next to it and see, wow, look at the difference. So that impact crater is far deeper than any kind of elevation that we're seeing expressed in that volcano. But in this profile, you can see that crater right at the summit of the volcano that's showing up in the profile there. That's neat.
So, Brian, so the moon has volcanoes and cracks in the surface. Does it also have faults like we have here on Earth?
Yeah, let's go to a really famous example, the lunar straight wall, also known as Rupus recta. There it is. See that long linear feature there.
So how can we tell, that this line here is not a crack, instead it's a moon lunar fault?
So it does look a lot like some of those extensional cracks that we saw before, but if we draw a profile across it, we'll see that it is actually a very different type of feature. And there you can see how the lunar surface is actually stepped up. And you can measure the height of that fault face. This is on the floor of Mare Nubium. It's an amazing, amazing area.
So, well, all this is all great. And these graphs really do help us visualize the details about lots of interesting lunar features here. But also, LMP has very impressive visualization tools that can take this, far more impressive levels. So maybe we can show it to you. Let's take a look of some of our tool. How about let's go to the Tycho crater.
Excellent.
As you can see that the Tycho crater had a center peak. That is a very interesting crater. And if we can draw a box that covers the peak area, and then we select a tool called the terrain viewer, and from there you can select different textures as well as different elevation maps.
Wow, so we're right now on the edge of the central peak. The graphs are good, but this is very impressive. So you're just walking along the terrain of the central peak there.
Oops.
See, parts of it are in shadow, parts of it are illuminated. Wow. That is some impressively steep terrain. And if you were planning a rover traverse, I would think it might be a little hazardous.
So from here, not only you can do the 3D fly over the crater, but we also have different layers that you can overlay, such as the slope layer. And from here you can see that there is a legend here. You can tell that how steep each area is. And so imagine if you drive a rover around this area, you certainly don't want it to go over to the slope that is the rover cannot handle. And also we can draw a line here you will be able to tell the elevations. So from here you can tell that you really don't want to take the rover up the slope in this kind of height. So these are just a few examples, and there are many layers such as temperature, chemical abundances, hazards like craters and boulders, and much more that you can explore with this tool.
So it's an amazing tool. Who is the audience for LMMP?
Well, there's actually a number of people that use these tools. A lot of mission planners will be able to use it to plan their future lunar exploration missions, and also educators such as faculties or teachers. They can use this tool to plan their classroom courses, and also the student will be able to benefit from learning about the moon features. And then also it is available to the general public as well, that they would like to explore the surface of the moon. And last and not the least is the scientists. They would be able to use these tools to do a lot of scientific research of the moon.
Fantastic, because the data that comes, and the data that is displayed in LMMP, the source of that, does that tie in directly to the planetary data system?
Yes, in fact, we get a lot of the latest LRO data directly from what they call the planetary data system, which is the archive for all the space explorations missions.
Fantastic. So this is a fantastic tool. It's great for scientific research or mission planning, but it's also a lot of fun. The moon is an amazing place. It's got incredible features, and this allows you to explore those features from the comfort of your own home. Thank you very much, Emily.
Well, thank you, Brian. This has been fun.